Welcome to this lecture number 9 of our course on fundamentals of transport processes. So far we have been discussing, initially we discussed vectors and tensors and their integral and differential theorems, and then we looked at some results that are obtained when these vectors operate on the velocity field, the fluid velocity field. In the last class we had discussed the rate of deformation tensor. It is a rather important subject, so we will briefly review it again before we proceed. So, this is the rate of deformation tensor. Second order tensor, it is the gradient of the velocity. It is also written as partial ui by partial xj. And if I were to write it in expanded form, then I would write it as sigma I is equal to 1 to 3, sigma j is equal to 1 to 3 of partial ui by partial xj ei ej. Okay. So, at a given point in the fluid, if I am at a location x and I go a small distance delta x to some new location, okay, I have a velocity at x and this is the velocity at x plus delta x. The difference in velocity delta u is equal to grad u, okay. Then I have a delta x dotting that. Okay. So, basically the displacement dotting with grad u, the dot product is between the displacement vector and the gradient in the rate of deformation tensor. Okay. So, this basically gives you the rate at which positions are moving relative to each other as the fluid flows. It is a second order tensor, it has 9 components. However, as we discussed in the last class, this can be decomposed into fundamental modes of deformation. Okay. So, the gradient, which is the second order tensor, can always be written as the sum of two parts. One is the symmetric part and the other is the antisymmetric part, okay, where the symmetric part is equal to half of the gradient of the velocity plus its transpose. The transpose is obtained just by interchanging rows and columns or by interchanging the two indices of the tensor, because one index represents the row, the other index represents the column. Okay. The antisymmetric part is equal to half of the matrix minus its transpose, okay, half the matrix minus its transpose. The symmetric part can once again be written as the sum of two tensors. One is a symmetric traceless tensor and the other is an isotropic tensor. Okay. The isotropic part is just proportional to the identity tensor. It has equal diagonal elements and 0 of diagonal elements. The symmetric traceless tensor is symmetric and the sum of its diagonal elements is equal to 0. Okay. So, this can be written as this symmetric traceless part plus 1/3 delta I j times partial. Okay. In the previous lecture, I had written this as the divergence of u. Partial u k by partial x k is also the divergence, because there is a repeated index. So, there is a dot product. Okay. So, this thing is a symmetric traceless tensor. What that means is that the sum of the diagonal elements of this tensor is equal to 0. Okay. And I showed you in the last lecture that the sum of the diagonal elements of this tensor is just equal to is Eii. Okay. Because if I have Eii and I expand it out using my indicial notation, there is one repeated index, that means there is a dot product. So, there is one summation and no unit vectors. So, this is just equal to summation I is equal to 1 to 3 of Eii, which is basically the sum of the diagonal elements of that matrix. Okay. So, this rate of deformation tensor can be separated into 3 parts. Okay. Is equal to the antisymmetric part plus the isotropic part, which was plus Eij, okay, the 3 parts. And I had shown you that there are specific forms of deformation associated with each of these 3 components. This tensor I have separated into antisymmetric, isotropic and symmetric traceless. And if you look at the local deformation corresponding to each individual part, okay, you find for the antisymmetric part, the deformation is basically a solid body rotation. Okay. That is, if I am sitting at some point within the fluid at that center and I look at the velocity with which nearby points are moving relative to the point at which I am sitting, you find that the nearby points are moving in a rotational form, that is, there is a solid body rotation around this central point. Okay. So, that is what is captured by the antisymmetric part of the rate of deformation tensor. Okay. And we saw in the last class that the rate of deformation tensor is related to the vorticity. Okay. So, the vorticity, which is the curl of the velocity partial u k by partial x j, that is the vorticity vector, can also be written as epsilon I j k times a k j. Okay. So, the curl of the velocity vector is also equal to epsilon double dotted with the antisymmetric part of the rate of deformation tensor. So, if I take epsilon and double dot it with the antisymmetric part of the rate of deformation tensor, I get a vector whose direction is perpendicular to the plane of rotation. Okay. So, that is what you get from the antisymmetric part of the rate of deformation tensor. Okay. In fact, you can actually, if I remember, in fact, there is a half here. Okay. There is a half sitting in front. Okay. Please note that. That is because the antisymmetric part has 2 partial u I by partial x j minus partial u j by partial x I. Okay. And once, just go back and check. Okay. You can see that there is, I should make a correction here, half of partial u k by partial x j minus partial u j by partial x k. This itself is the antisymmetric part. Okay. So, there should be no half in front here, okay, because half of the difference between these two is just the antisymmetric part. Okay. So, please correct that in the previous lecture. And I had written a half here. Okay. So, that half should not be there. Okay. So, that is the antisymmetric part of the rate of deformation tensor. The second part was the symmetric traceless part, okay, and that I am sorry, the isotropic part, and that, as I showed you, corresponds to radially outward or inward flow. Okay. If the divergence of the velocity is positive, that means that the flow is radially outward. If the divergence of velocity is negative, the flow is radially inward. Okay. And this divergence of velocity is non-zero only if you have a source of fluid. Okay. As I said, the volume has to increase for the divergence to be non-zero, because the divergence of velocity integrated over a volume is equal to integral of u dot n over the surface. So, if that is non-zero, that means there is net fluid coming out of that surface. Okay. So, there has to be a source, okay, or the density has to decrease. Okay. So, unless if the density is remaining a constant and there is no source of fluid, then this part will be identically equal to 0. And the third part was pure extensional strain. Okay. We had seen in the last class that this resulted in a deformation in which you have expansion along two axes and compression along the perpendicular two axes. Okay. So, there is expansion along two axes, compression along the perpendicular two axes. Okay. So, there is one extensional direction and one compressional direction in two dimensions. So, that if I have some differential volume here, okay, and if I look at what this extensional motion, how that will deform this differential volume, after some time I will have the volume looking something like this. Okay. It is going to deform in such a way that it extends along one axis, compresses along the other axis, in such a way that the area is preserved in two dimensions or the volume is preserved in three dimensions. Okay. And these two extension and compression axes also do not rotate, okay, because rotational motion is associated with the antisymmetric part. So, the symmetric part has no rotational motion. So, the axes remain the same. There is no increase in volume because the trace was 0. Okay. Because of that you cannot have an increase in volume. So, it deforms in such a way that volume is preserved as well as there is no rotation. So, that is what is represented by the symmetric traceless part of the rate of deformation tensor. Okay. This is a simplified picture in two dimensions. If you go to three dimensions, you have a symmetric traceless tensor, which is a 3 by 3 matrix. Okay. Similarly, the antisymmetric part is also a 3 by 3 matrix. For the antisymmetric part, this still holds. Note that what I have written here is for 3 dimensions, this 1/3. In the last class, I showed you that for 2 dimensions, it is equal to 1 by 2. So, in general, it is equal to 1 by d, where d is the dimensionality of the system. Okay. So, in 3 dimensions, these deformations can be of different forms. Okay. So, Eij is a symmetric traceless tensor. Okay. Okay. So, it is symmetric E11, E12, E13, E12. Okay, so, it is a symmetric tensor and the sum of the diagonals are all 0, E11 plus E22 plus E33 is equal to 0. Okay. Symmetric tensor, it is self-adjoint. Okay. This transpose is equal to itself means it is a self-adjoint matrix. That means that it has its eigenvalues are real and eigenvectors are orthogonal to each other, and the eigenvectors form a complete basis set. Okay. So, the eigenvalues of this tensor basically represents the rate at which there is stretching or compression along the principal directions. The eigenvectors represent the 3 principal directions along which there is deformation. Okay. So, for example, in a flow field, you know that the eigenvectors of this symmetric matrix at each and every point in space are all orthogonal to each other. That means that if I have one particular point in space, I have 3. Okay. In the most general case, I will have 3 perpendicular directions, okay, represented by the eigenvectors at this point in space. So, there are 3 perpendicular directions, okay, at one point in space. Okay. So, there are 2 in the plane and 1 that is coming out of the plane. Okay. And along each of these 3 perpendicular directions, I have one eigenvalue. Okay. Along each of these 3 perpendicular directions, I have one eigenvalue, which basically gives you the rate at which there is extension or compression along that particular direction. Okay. Note that this is a traceless matrix. That means that the sum of the diagonal elements is equal to 0. Okay. And we know from linear algebra that the sum of the diagonal elements is also equal to the sum of the eigenvalues. Therefore, the sum of the 3 eigenvalues has to be equal to 0. Okay. just a reflection of the fact that volume is preserved. So, either you have to have stretching in one direction, compression in the other directions in such a way that volumes do not change. Okay. So, therefore, you can have either 2 positive eigenvalues and 1 negative, you could have 2 negative and 1 positive, or you could have 1 0, 1 positive and 1 negative. Okay. If I have 1 positive eigenvalue and 2 negative eigenvalues, okay, that means that at this point along the 3 principal directions, okay, I am having extension in one direction and compression in the other 2 directions, okay, because you have 2 negative eigenvalues and 2 and 1 positive eigenvalues. So, basically flow is coming in from 2 directions and is going out along the third direction. Okay. So, this is called uniaxial extension. There is extension along one axis and there is compression along 2 other axes, if 2 eigenvalues are negative and 1 is positive. Okay. The other option is for 2 eigenvalues to be positive and 1 to be negative. Okay. So, in that case you have stretching along 2 directions and compression along the third direction. Okay. You have stretching along 2 directions along the positive eigenvalues and compression along the third direction in such a way that the divergence of the velocity is equal to 0. Okay. So, in that case you will have flow that looks like this. Okay. It will come in along one direction and it will flow out along 2 directions. The only other option is to have 1 0, 1 positive and 1 negative. If all 3 are 0, of course, there is no deformation. Okay. So, you can have so that is a trivial case, but you could have 1 positive, 1 negative and 1 0. Okay. In that case you have deformation that is coming in along one direction, it is going out along one direction and there is no deformation in the third direction. Okay. So, therefore, you just have fluid that is in the plane. Okay. The same figure that I showed you in the previous lecture, this one, okay, deformation in the plane, that is when the third eigenvalue is equal to 0. Okay. And the other 2 have to be opposite in sign and equal in magnitude. Okay. So, you just have fluid that comes in this way . Okay, deformation in the plane. Okay. So, this is called uniaxial extension, extension along one axis. This is biaxial extension. And this is what is called planar. Okay. So, these are different components of the rate of deformation tensor, and as we shall see a little later, rotation, solid body rotation does not change the distance between nearby points in the flow. Okay. So, there cannot be a stress due to the antisymmetric part of the rate of deformation tensor. If the fluid is compressible, the isotropic part of the rate of deformation tensor is identically equal to 0. So, all of the stresses have to be only due to the symmetric traceless part of the rate of deformation tensor. One more topic in kinematics before we proceed to deriving equations of motion, and that is the substantial derivative. Now, when you take the partial time derivative, implicitly you are keeping the position the same and finding out the change in property when between two subsequent instants of time. Okay. So, the partial, so for example, if I have a temperature field in this 3-dimensional system, partial t with respect to temperature is equal to limit as delta t goes to 0 of t at x1, x2, x3, t plus delta t minus t at divided by delta t. Okay. So, that is the partial derivative, the difference in temperature between two time instants divided by the time interval in the limit as that interval goes to 0. However, if you have some kind of a fluid flow, if you have some kind of a fluid flow that is taking place, if I have some differential volume that is here at time t, after a small interval of time it would have traveled to some other location. Okay. It would have traveled and it would have deformed. Okay. So, it would have traveled to some other location x plus delta x. Okay. That is because the mean fluid is carrying the properties along with it. Okay. The temperature is traveling along with the fluid itself. You have a hot parcel of fluid and there is a mean flow, that parcel is actually being convected by that mean flow. Okay. So, in order to find out what is the temperature difference along a moving parcel of fluid, this partial time derivative is not the appropriate derivative, because this is in a fixed reference frame. Okay. The fixed reference frame is what is called an Eulerian reference frame. That is, it is fixed in space. On the other hand, a reference frame that is moving with the mean fluid velocity is what is called a Lagrangian reference frame. Okay. Okay. So, in the Eulerian reference frame, you would write the temperature as some function of position in time, absolute position and absolute time. At each instant in time, you just find out what is the temperature for that given position. Okay. In the Lagrangian reference frame, you write it down as a function of the moving parcel of fluid that is carrying its temperature along with it. Okay. So, in this case, you write it as t as a function of because the location of that parcel itself is now a function of time. It has some one value at this instant, one value at that instant, and it is moving in space, and therefore, it is carrying the temperature or the concentration along with it. Okay. So, that is the Lagrangian reference frame. Now, in order to implement a Lagrangian scheme, one has to know if a parcel of fluid is at this location at one instant of time, where it was in the past. Okay. What was the past location of that parcel of fluid, which is at one particular instant at this present location. Okay. That is usually a difficult task, because you have to trace out the entire history of the fluid. Okay. However, one can define a derivative which is called the substantial derivative, which contains in it the elements of the Lagrangian moving reference frame. Okay. And that is, if a fluid element was at some location x at time t, after the time t plus delta t, it has moved to a new location. Okay. So, the difference in temperature between the location at t plus delta t minus at time instant t plus delta t minus the temperature at location x at time t. Okay. So, that is the how the substantial derivative is defined. Okay. So, let us look at that. Okay. It is usually written as dt by dt. Okay. It is equal to limit as delta t goes to 0 of t at x plus u delta t, t plus delta t minus t at x t. Okay. Note that I am taking the position x plus u delta t at time t plus delta t. Why is that? Because if the fluid element was at location x at time t, at time t plus delta t, it has moved a small distance. At time t plus delta t, it has moved a small distance to some new location x plus delta x. What is that new location x plus delta x? The new location, the displacement, is going to be equal to the velocity times the time interval. Okay. The distance moved is going to be the displacement vector is going to be equal to the velocity vector times that time interval. Okay. So, you are taking the difference in the temperature between x plus u delta t and t plus delta t minus t at x t divided by delta t. Okay. So, that is a substantial derivative, the derivative in a reference frame that is moving with the parcel of fluid. Okay. And you can easily evaluate this in terms of the partial derivatives by just using the chain rule for differentiation, okay, because x1 plus u1 delta t, okay, at time t plus delta t minus x1 and t at time t. Okay. So, you just evaluate it by taking partial derivatives. Okay. And what you will get is this is partial t by partial t plus u1 partial t by partial x1 plus u2 okay, because the distance travelled was u1 delta t. Okay. So, therefore, the difference in temperature is equal to u1 delta t times partial t by partial x1, and then I divide by this delta t in the denominator, okay, divide by this delta t in the denominator, okay, and therefore, I get u1 times delta t partial t by partial x1. So, this is the substantial derivative which recognizes the fact that fluid elements are moving along with the mean velocity of the fluid. Okay. I can also write this in vector notation as partial t by partial t plus u dot grad t. Okay. Partial t by partial t u dot grad t is u1 partial t by partial x1 plus u2 partial t by partial x2 plus u3 partial t by partial x3. So, this is the difference in temperature between the location x plus delta x at time t plus delta t minus the temperature at location x at time t. Okay, that is this substantial derivative. In a moving fluid, if for example, the temperature does not change with time for a moving parcel of fluid. Okay. In other words, if I were to neglect completely the diffusion or the conduction of temperature, if the temperature is a constant on a moving volume element of fluid, then this derivative is 0. Okay. If the temperature is a constant on a moving element of fluid, it is a substantial derivative that is 0, not the partial derivatives. That is because as the fluid moves, this volume element that was at location x goes to x plus delta x. Some other fluid occupies the location x, and there may be spatial variations, okay, between nearby volume elements of fluid. If it is if the temperature is not diffusing, then the temperature on a moving element of fluid is constant. It may be spatially varying. So, in that case, it is the substantial derivative that will be 0. The partial derivative in general will not be 0. Okay. So, that is the substantial derivative. It is in a Lagrangian reference frame, and it recognizes the fact that as the fluid moves, the fluid element occupies a new location, okay, after an instant of time in comparison to the original location, and you are taking the derivative on that moving volume element of fluid. Okay. So, next we go down to start deriving the conservation equations. Okay. In the previous lecture course on fundamentals of transport processes 1, we did this by actually writing out a differential volume in different coordinate systems, looking at what comes in and what goes out, and writing the balance law. Okay. The net change in the mass, the heat in a differential volume is equal to what comes in minus what goes out plus source minus sink. Okay. Rather than do it that way, what we will do is to look at the rate of change of mass on a moving differential volume without reference to a specific coordinate system. Okay. So, for that we have to do some background work. if I have a volume, okay, dV, okay, with the surface ds, okay, there is a volume dV with the surface ds on the surface. Okay. The net mass within this volume is going to be equal to integral over the volume dV of the density within that volume. Okay. There is a net mass within the volume. Okay. The mass conservation equation basically states that the mass within this volume has to be conserved. Okay. The volume itself is moving as a function of time. Okay. So, let us take this volume dV. Okay. I will draw it bigger over here. Okay. This is the volume dV with the surface ds. Okay. Now, this volume itself is a function of time. Okay. This volume itself is a function of time. This is a fluid material volume. Okay. And as time progresses, okay, the fluid particles within this volume will move, okay, and those on the surface will also move. Okay. Okay. The fluid elements on within this volume will move as a function of time. Those on the surface will also move. Okay. So, at some later time, at some time t plus delta t, this volume would have gone to some other location. Okay. The surface is the volume itself is defined by the motion of the surface points. Okay. The points on the surface, how they move. Okay. The points on the surface move with the same velocity as the fluid velocity on the surface. The points within move with the same velocity as the fluid velocity within this volume. Okay. Note that the velocity is a vector that is defined at each point in space. It is a continuous field. Okay. Now, as this volume moves, the points that are on the surface will continue to be on the surface, provided they are moving with the same velocity as the fluid velocity at that point. The points that are within will continue to be within, once again provided they are moving with the same velocity as the fluid velocity at that point. Okay. What that means is that the points on the surface continue to be on the surface, the points within continue to be within. Okay. That is because the fluid velocity, as I said, is a single valued function of position. Okay. At each point, the fluid velocity has only one value. Okay. If a point within has to cross and go outside the surface, then obviously the velocity, it has to intersect with the trajectory of a point on the surface. Okay. If a point within has to travel and go outside the surface, okay, it has to intersect with the trajectory of some other surface point, okay, that is traveling on the surface. Okay. If it has to go from outside to inside. Similarly, if a point that is outside has to come inside, it has to cross trajectories. This crossing of trajectories is not permitted, because at that particular location it implies that the velocity has two values, okay, whereas we have defined the velocity vector as a single valued function in space. Therefore, fluid points cannot cross, okay, from inside to outside the surface, because the surface is moving at the mean velocity at that location at the surface. Inside is moving at the same mean velocity as the inside points. Okay. And if it has to cross, it will be a double valued function, which it is not. Okay. It is a single valued function at each point in space. Therefore, one cannot have the crossing of trajectories. Okay. What is outside, what is inside, and what is on the surface continues to be on the surface, provided it is a material, okay, point which is moving with the same velocity as the fluid velocity on that surface. Okay. And within this moving surface, the mass is defined as the integral over this volume, which is a function of time, okay, of integral dV times rho. Okay. Now, the rate of change of mass, okay, is equal to the time derivative of the integral over this volume of dV times rho. The rate of change of mass is the time derivative of the integral over this volume of dV times rho. Okay. Now, the volume itself is a function of time. The density also is in general a function of time and space. Okay. So, you are going to get contributions to this derivative both from the volume, the dependence of density on time, as well as from the fact that the volume itself is changing, okay, as time progresses. Okay. Now, how do we combine these two values? Okay. So, there are two contributions to this rate of change of mass. Okay. We know that from mass conservation equation, the mass within that volume has to be conserved, because points that are inside continue to be inside, points that are outside continue to be outside, and therefore, I require that for mass conservation condition, this has to be equal to 0, the rate of change of mass, okay, because mass cannot be created or destroyed unless you take into account nuclear reactions, for example. Okay. So, we will work within the classical regime where this has to be equal to 0. And this relation that I have got is for a moving element of fluid, and I need to convert that into a relation for a fixed volume element. Okay. So, let us do that. Okay. So, we go back to what we had earlier. Okay. We have this volume. Okay. This is the volume at time t. Okay. And after a little bit of time t plus delta t, this goes to some other volume. This is V at t plus delta t. Okay. What is the change in this integral dV times rho between t and t plus delta t? Okay. There are two components to this change in the volume, change in the mass. One is because the density within the volume itself is changing. At various points within the volume, you have a density that is defined. That density within the volume itself is changing, and the other is because the surface itself has moved. Okay. So, there are certain parts of the surface that have come into the volume which were not previously in the volume. Okay. That has to be incorporated into the mass within this volume. There are certain parts of the surface that were previously within the volume, but have now left. So, that has to be subtracted from the mass. Okay. So, there are two contributions. One is due to the change in density within this volume itself. The other is because certain regions have come in and certain other regions have left. Okay. So, the change in mass due to the volume, the change in density itself is just integral dV of partial rho by partial t. Okay. So, that is the change in mass because the density is changing within this differential volume. Okay. In addition, there are certain parts that have come in and certain parts that have left. Okay. So, for example, if I expand out a small region over here, okay, a surface which was initially at this location has now moved to a new location. Okay. Surface which was initially at this location has moved to a new location because of the fluid velocity. The fluid velocity could in general be in some direction at this location. Okay. This is the fluid velocity u in some general direction, okay, with respect to the surface. Because the fluid is moving, the surface has also moved. Okay. So, if you take this little patch of surface, I will call it as ds. Okay. Because of this little patch of surface, how much of volume has come in to this differential volume, because the surface has moved in this way. Okay. The volume that has come in is basically equal to this distance, okay, which is the perpendicular distance of the surface, okay, the perpendicular distance that the surface has travelled. Okay. That is this perpendicular distance, okay, that the surface has travelled. Okay. What is the perpendicular distance that the surface has travelled in a time delta t? Okay. Perpendicular distance travelled is equal to the velocity along the perpendicular times time. Okay. So, the perpendicular distance travelled is equal to the velocity times time, the velocity along the normal direction. Okay. So, the velocity along the normal direction is u dotted with n times delta t. Okay. So, that is the distance that is travelled. Note that u dot n is a velocity, it is the normal velocity. The component of the velocity u along the unit normal to the surface n. Note that this is the outward unit normal to the surface. So, that is the distance travelled. Okay. The total volume that has come in is equal to the distance travelled times that surface patch. Okay. So, the total volume that has come in, okay, into area. So, the volume that has come in is this times ds. Okay. So, there is a total volume that has come in because the surface is travelled. Now, the mass that has come in is just equal to this times the density itself, density at that particular location, okay, the density at that particular location, that is the mass that has come in. Okay. So, therefore, the mass in, okay, let me just get rid of this, so that we can write it all in the same. Is equal to rho ds times u dot n delta t. That is the mass that has come in for this little patch of surface. It has travelled a distance u dot n delta t. Okay. So, that is the mass in a time delta t. Therefore, the rate of mass in is going to be equal to this mass in divided by the time. So, this is going to be equal to rho ds u dot n. Okay, this is the rate at which mass is coming in for this little patch of surface, because the surface is moving. Okay. Now, if you take a patch of surface on the other side, okay, if you take a patch of surface on the other side, this surface initially it was something like this. Okay. So, if I take this little patch, okay, this surface initially it was here, and after some time it goes to some other location. Okay. After some time it goes to some other location. Okay. So, obviously, some volume elements have left this volume. Okay. It has left behind some volume as it is travelling in this direction, okay, and therefore, the mass has left this volume. Okay. Mass has been reduced from this volume. Okay. What is the mass that is reduced? Okay. The argument is exactly the same. Okay. I take this little patch of surface. Okay. Now, the outward unit normal is in this direction. That is the outward unit normal at that point on the surface. Okay. It is in this direction. Let me plot it on the original surface for simplicity. Okay. The outward unit normal is in this direction, and the velocity vector is in some direction like this. Okay. U vector is in this direction. Okay. The amount that is left is once again u dot n ds. Okay. There is a rate at which mass is left, okay, except that now u dot n is negative, because u and n, the angle between them is greater than 90 degrees if the volume, if the velocity is going to be opposite to the unit normal in such a way that there is some volume that is left behind as the surface moves. Okay. So, therefore, for volume elements that are leaving the surface, u dot n is automatically negative, because the velocity is in opposite, the component of the velocity along the unit normal is along the inward unit normal. Okay. It is opposite to the outward unit normal. So, u dot n is automatically negative, and therefore, rho s, rho ds times u dot n will automatically be negative. Okay. And therefore, this expression gives you the rate at which mass comes in and mass goes out. Okay. If mass is coming in, and if you define n as the outward unit normal, u dot n will be positive, that will add mass to the volume. If it is leaving, then u dot n will automatically be negative. Okay. So, this is the second component. For each patch of surface ds, we get this. Therefore, the total is just going to be equal to integral over the surface of rho u dot n. Okay. So, there are two components, one because there is a change in density within this volume itself. The other is because as the volume is moving in space as a function of time, there are elements, volume elements that are coming in to this differential volume, there is volume elements that are leaving this differential volume. Okay. This thing is what is called the Leibniz rule. Okay. Okay. This identity, okay, that integral dv rho over something that is function of time. Okay. This is called the Leibniz rule, and it works not just for density, but for all other things. Okay. It works for momentum, for energy, and so on. In all such cases, you have a change in that quantity because one, that quantity is changing within the volume itself. Second is because as the volume is moving, there are certain regions that are being swept in, and there are certain regions that are being left behind. And so, you have to account for both those regions that are being swept in as well as the regions that are being left behind. Okay. And that those regions that are being swept in and the regions that are being left behind are incorporated in this second surface integral term. Okay. They are both incorporated in this second surface integral term. Okay. So, that is the Leibniz rule. Okay. And we know that the rate of change of mass has to be equal to 0 for mass conservation. Okay. Integral v of t dv times rho, the rate of change of that, okay, which I had derived as integral dv times partial rho by partial t plus integral of the surface ds of rho u dot n. This has to be equal to 0. Okay. For the second term here, I can use the divergence theorem. Vector dot n integrated over a surface is equal to the divergence of that vector integrated over the volume. Okay. So, this integral dv partial rho by partial t plus integral dv of del dot rho u, this is equal to 0. And this has to be true for every volume within the fluid, okay, because it is true at each and every point within the fluid, and therefore, it has to be true at every if it is true for each and every volume that I can consider, this is true at each point within the fluid. Okay. And that means that the mass conservation equation partial rho by partial t plus del dot rho u is equal to 0. Okay, so that is the equation for the conservation of mass. In indicial notation, I will write this as partial rho by partial t plus partial by partial xi of rho ui is equal to 0. Okay. Dot product repeated index, it is a scalar equation for the density. I can also write it as use differentiation by chain rule to write this as this differentiation by chain rule, and you can identify these first two terms as the substantial derivative. Okay. These first two terms are identical to the substantial derivative. So, I can also write this as d rho by dt plus rho partial ui by partial xi is equal to 0. If the density is a constant, then d rho by dt in a moving reference frame has to be 0, and therefore, I have the mass conservation equation for constant density, okay, incompressible. Density is a constant. I have partial ui by partial xi is equal to 0, or the divergence of velocity is equal to 0. Divergence of velocity is equal to 0, as I just discussed, the isotropic part of the rate of deformation is tensor is 0. There is no radially outward or inward flow. Okay. One can derive other conservation equations just as easily. If I wanted to derive an equation for concentration field, Okay. What I would say is that for this moving volume element, okay, okay, d by dt of the integral dV times the concentration of the solute, okay, the concentration of the solute, okay, in this moving reference frame is equal to an integral over the surface, okay, is equal to an integral over the surface of the flux, okay, okay, times the unit normal. Okay. So, if I have some volume element which is moving and I have some flux on the surface, okay, then d by dt of the integral of the volume times the concentration is equal to the net flow into this volume, okay, due to the fluxes acting on the surface. Okay. The flux will increase the concentration within this volume if it is directed inwards. Okay. So, concentration, so the mass within this volume is going to increase if the flux is directed in the direction opposite to the outward unit normal. Okay. The mass within this volume is going to increase if the flux is directed outward along the inward unit normal or opposite to the outward unit normal. I have defined my unit normal n as the outward unit normal in this case, and therefore, this is equal to minus integral over the surface of q dot n. Okay. When q dot n is negative, the mass increases. Okay. So, when q and n are in opposite directions, the mass increases. So, this is equal to minus integral over the surface of the mass flux, that is the amount of material coming in per unit surface area per unit time. Okay. Simplify this using the Leibniz rule once again. Okay. I get integral dV of partial c by partial t plus integral ds of c u dot n minus integral over the surface of q dot n. Okay. And now, we use the divergence theorem for both the convective part as well as for the flux. Okay. So, then I get integral dV partial c by partial t plus integral over the volume of the divergence of concentration times the velocity is equal to minus integral over the volume of the divergence of the flux itself, of the flux, okay, the divergence of the flux. Okay. And this has to be true for each and every differential volume. That means, it has to be true at each point in space, and therefore, the concentration equation becomes partial c by partial t plus minus partial q I by partial x I, okay, or dc by dt plus del dot u c is equal to minus the divergence of q. Recall, we got exactly the same expression by doing our differential balances over volumes in the fundamentals of transport processes 1. There we did differential balances over cubic volumes, spherical volumes, cylindrical volumes. In this case, we get the exact same expression without reference to any underlying coordinate system. Okay. And then we have a constitutive relation for the I should use J for the mass flux. Let me just use J for the mass flux to avoid any confusion. Q is better used for the heat flux. Okay, so this is J, this is J I, this is J, and this is del dot J. And then we have the constitutive relation. J is equal to minus d times the gradient of C, where d is the diffusion coefficient, okay, and the flux is in the direction of decreasing concentration. So, it's opposite to the gradient vector. Gradient vector gives you the direction in which there is a maximum increase in concentration. And the constant of proportionality is the diffusion coefficient with dimensions of length square per time. Okay. And so, from this you will just get the equation partial c by partial t plus del dot u c is equal to the divergence of d grad c, and is equal to d times the Laplacian, provided if the diffusion coefficient is independent of position. It is equal to d times the Laplacian if the diffusion coefficient is independent of position. Okay. And this is the exact expression that we got for the concentration equation in the previous course. Okay. Similarly, one can get an expression for the temperature equation, and if I write it out in this, but in this form we will get rho Cv into partial T by partial T plus T by dxi of u times T is equal to of K partial T by partial xi. Okay. Or alternatively rho Cv into plus del dot u t is equal to del dot K grad T. And in case the thermal conductivity is independent of position, this can also be written as del square, okay, where del square is the Laplacian. And I had shown you in the previous lecture how you derive the Laplacian in the different coordinate systems, spherical, cylindrical, as well as Cartesian. In spherical and cylindrical, you have to account for the fact that the unit vectors depend upon position, and therefore, the dependence of unit vectors on position has to be taken into account, and we derived explicit expressions for each of these. Okay. So, these are the mass heat conservation equations. Note that in the previous course, we had actually taken a differential volume, taken its surfaces, 6 of them, found out what came in, what went out, and on that basis determined what the conservation equation was. Whereas, in this case we did not have to do any of those. We just used the divergence theorem, okay, and used the fact that the Leibniz rule can be applied for a differential volume, okay, in order to relate the change in a moving reference frame to that in a fixed reference frame. And that is all we required in order to find out the conservation equations. So, the next step is to proceed and determine conservation equations for the fluid momentum. This procedure, as you can see, is much simpler. Had I done it the way that I had done it previously, I would have to have 3 components of momentum, and for each of those I would have to have 3 components of fluxes. Whereas, here I am just going to treat both momentum and flux as objects in themselves, independent of the underlying coordinate system. So, we will proceed with the conservation equations for momentum for the fluid in the next lecture. So, kindly review what we have done here, that is, how do you relate the changes in a moving reference frame to that in a fixed reference frame, and we will proceed in the next lecture to deal with fluid momentum conservation equation. So, we will see you then.